Okay. If I could only think, that would have been the opportunity. Yes.
So today I asked itself to, in some sense, construct the inverse. So the talk yesterday was not recorded anyway. And from today it will be okay to record all the talks. And also I asked itself to explain a little bit more about the basic tools and so on. But the idea to get in student instead and start research. Okay, so.
Okay, thank you very much. Yesterday I talked about, I end up my lecture by talking about blowing up. And so I should mention where it is used for. People also asking me where is my notes. I'm following some notes in book from my website. You can go to my website. So there's number 1 is the book. Here's a book. So and then I'm doing most number 2, number 22. There are papers there about classification of isolated singularities and algebraic equations of PL manifolds or general characterization of algebraic sets. This is like an elementary introduction in number 20. It's a lecture notes from the assignment mathematics, where the book is like more advanced version of this. And number 22 is about algebraic cycles. Is not too difficult to follow. So at the time being, I've been using this thing. I will use these things. Blowing up, I talked about blowing up last time. I should mention, of course, almost everything I did is a joint work with Henry King. Since this is being recorded, I should send a message. Henry, you should come back. You took a long vacation. You should come back. Let's finish this program. So this is the program I started with Henry King 43 years ago. We worked on it 30 years. There are still open ends that I'm hoping it will be finished. And from this, there are some interesting problems came out. Hopefully, I will talk about them. So blowing up. So in the book, first section of the book, there are examples. You write equations, and then you can blow up to make it non-singular. There's also a book I wrote called 4 manifolds. There is blowing up complex singularities are mentioned. So there's an example. I do there x squared plus y cubed plus z to the 5 equal to 0. This is in C3. So there's an example. I did it just for beginners. You can blow up. There's also the book by Hirzebruch, Koh, and Neumann. Very nicely blowing up complex singularities mentioned. So you can, by combining these things, you can make a lot of examples. So the theorem is used from blowing up is by Hironaka. If you have an algebraic set, this is non-singular algebraic set, and this is an algebraic set. There exists algebraic multi-blow up. It means you blow up these things along smooth centers many times, one after another. When you where the strict image free image is a non-singular algebraic set. Strict pre-image is, so this is a non-singular variety V, and you have M, a singular variety in here. You blow this up, so this becomes V tilde. Many times, I mean, I'm not putting the details. These centers could be, they are blown up along centers, smooth centers, so they are blue. So you take a smooth submanifold in here, you blow this along that, take another smooth manifold of this. All these centers are smaller dimension than the dimension of M. And at the end, this thing turns into smooth. Every time you blow up a center, you introduce a divisors. These are called divisors. Like when you blow up point in the plane, you get a RP1, a circle. So these are called divisors. And this is strict pre-image, this thing, M tilde. So, by doing this, you can get this manifold, the variety to be non-singular. And then there are many versions of it which we use in our work. So this is the principal technique we use, topologically classifying real algebraic sets along with complexification. So there's a notion of fine and stable. Fine means, so I will say by words. In a variety, fine means it is an intersection of transverse intersection. A component. So this algebraic set is called fine if you can find smooth non-singular algebraic sets transversally intersecting one of the components. This is fine. Stable means you have each is codimension 1. So you can find codimension 1 non-singular variety, codimension 1 non-singular variety, codimension 1, condimension 1, and finally this will be hypersurface here. So that's fine and stable. Okay, so you can go back, work this theorem, Hiranoko's theorem. You can arrange all the centers that you blow up to be fine, for instance, or stable. Where we use this, I mean, I think we use them when we try to get topological applications of this theorem. For instance, you have two algebraic cycles. You have two algebraic cycles, another one. You want to find their intersection. You want to do cap product or something. You want to move them. This is called moving lemma or something. Algebraic geometers do this in different contexts. What we usually do is we blow up, we take this theorem such that every center is, for instance, fine or stable, and then you can move this algebraic set. If all this algebraic, you can move this algebraic set inside of this by epsilon moves. Why is that? Because remember what I told you. You have, so the very first stage, M will look like this. M will look like this in VR. And you know that you can move this to an algebraic component of an algebraic set. Remember I told you, if you have a codimension 1 smooth submanifold, you can move it to algebraic set if the homology class is algebraic. If it's not algebraic, you can just move as a component of an algebraic set, like this. So then in next thing, you can move VR inside of VR plus 1. I mean, here I think you can move. Suppose you want to move this to some smooth manifold, still algebraic. Because this is algebraic homology class inside of this non-singular algebraic set, of course you can do that from the theorem I mentioned last time. Because this homology class, it's in the same homology class. Then you can move, the big thing is, this is an algebraic subset of this. I can move this with epsilon because that homology class in here represents my algebraic cycle. You can move it. So you can move everything a little bit. So you can put this, things in general position. So this is how we do, cup products are well defined, the algebraic homology in applications. Okay, also last time I mentioned, so this is an algebraic set, and I sitting in Rn and sitting in Rpn. So this is a picture of Rpn. I said that you can, by blowing, this is like an algebraic set V in Rn. I said you can make an algebraic set in Rn. Projectively closed by blowing up. I kind of told you what the proof is, and proof is like this. So the Rn sits inside of Rpn. This is my algebraic set inside of Rn, but when you go to Rpn, you might have some other component appearing in here. Projectively closed means no other component appearing in Rpn, so this is Rpn minus 1. So the no piece, all algebraic, so the complement of Rpn minus 1 is Rn. So when you take the algebraic closure of it, if nothing appears in here, it's projectively closed. If something appears in here, because this is codimension 1, this intersection is even lower codimension, so lower codimension, okay? Then you blow up. I mean, you have a smooth, for instance, non-singular algebraic set and smaller dimensional things. Then you're blowing up. You can make them disappear. When, after this process, if you have some small dimensional things in here, when you blow that up, they will be part of this normal divisor things. They will disappear. So that's the idea when by blowing up the Rn, you can make this projectively close. Basically, you put this inside of projective space, then you stuff that appears lower dimensional things. By blowing up whole thing, you get you make this lower dimensional things disappear. And blown up things sits inside of, this after you blow up. So this is blow up thing. This sits inside of Rn plus some R. The K is very large, or product of Rp case. And then since every projective variety is a affine variety, then you embed in the affine space projectively close. So that was the idea. So I'm repeating what I said last time. Also, I mentioned one technique last time. Is there any questions up to here? I'm told that I make it understandable to grad students, but this is a difficult theorem, of course. I always want to understand this. I always understand a little part of it. And recently, Bierstone and Millman made the original proof is very difficult. There's a proof by Bierstone and Millman, a little bit more understandable. And most recently, there was a conference in Gokova. There's a young Polish topologist, Wojciech, I forgot his last name. He's in Purdue. And he has even more concrete approach to this. What you have to do it by, what's his name? Wodarczyk. Yeah, basically by blowing up, you make some complexity less. And then his approach is complexity is not a number, complexity is whole situation. So he takes this blow up the data, he assigns some complexity rather than very concrete number, but then it's easier to keep track of it. It's been some years, he was in Gyoko, so probably it became more understandable theorem right now. So I'm still hoping to understand this because one of the open problems is related to this. Okay. Also, last time I used the following fact, so I'll make it understandable, grad students. I took some a compact set, and L is a non-singular algebraic set. And I have a map from compact set to reals here, such that f L is an entire rational function. Then you can approximate this by polynomial. Everyone, I mean, this is a smooth function, of course. This is smooth. Everyone knows how to approximate smooth function by polynomial or rational function. You can, but with the proviso that P, U, this which was U, P also, this new, the approximation you got has also this property. It didn't move this value. F was in here was an entire rational function. After you approximate it, a polynomial has the same property, it's the same entire rational function. And this is very, I mean, I use something like this when proving codimension 1 case. Now I'm told to make it understandable grad students. I think you can just take this one to start with. This is a smooth function, which is 0. This is a value restrict. This is 0. So once you have a smooth function, which vanishes on the non-singular set, you can write this. You can write this AI, BI. These are smooth. BIs are in the ideal of polynomials defining L. I mean, think of like L is a point. If you have a smooth function vanishing at the point, you can of course write a function x times something, some other function. Basically what it is. So you assume L is like a coordinate hyperplane. If it's vanishing there, locally you can write this as a combination of smooth functions on the ideal of function defining L. Then you approximate by polynomial. Then you approximate this by polynomial AI prime. Then you write your P by definition. You say U plus AI prime beta I. So that's how you get this. So I used it last time. I made this understandable. Now let me prove a normalization theorem, which will imply that every closed smooth manifold is a component of an algebraic set. So I will prove sequence of theorems like this. You know, a smooth manifold is a component of an algebraic set. It's a non-singular points of algebraic set. It is a non-singular points of algebraic set, not abstractly, but even in given Euclidean space. And I will keep improving this. So this is the first version. So the proposition. Nash proved that every closed smooth manifold is diffeomorphic to component of an algebraic set. And I think that the non-trivial part of his proof is some normalization, not the transversality part, there's a normalization, and the misunderstood part. And that's the part we improved upon such a way that we can generalize this for not just component, for all algebraic set, and then you do it without stabilizing, right, in Rn. So this theorem like this, so I have a L, okay, compact, a compact set. This is a non-singular algebraic set. Just like in here, K in L. And the sitting is inside of Rn. Okay. Then there exists algebraic set. Rn cross Rn. I mean, let's see. I just want to say one more thing. And the function k to w is a non-singular algebraic set. Inside of some Rm. So these are what's given. Then there exists an algebraic set Z Rn and P, a polynomial okay. I mean, this smooth function should, I can, for instance, require a property like this. If this smooth function is already a polynomial on L, I can demand same thing from here. So and if L is a polynomial, then there's a polynomial P approximating F, keeping L fixed. So the picture is something like this. Maybe I draw a picture here. So that's my Rn. And then I have a K. This is my K, compact set. And then I have a non-singular algebraic set L. And I have a function from here, F, to W. This is Rm. This is non-singular algebraic set. So I have a map from K to W. Then I can find an algebraic set inside of Rn cross Rm. So this thing is like Rn cross Rm. This is my Z, it's algebraic set. Make it a little bigger. Here. And I have a map from here, from Z to P. I want to say, what do I mean by F approximating P? There's a projection. There's a projection pi. Okay. And there's a piece of this lying here. So that just means there exists a smooth diffeomorphism. I think there's a smooth function. There's a such that you tilde. So there exists a smooth phi. This is the graph of phi. And this is a diffeomorphic to U. So here's a picture. This is my U. U is a little tubular neighborhood of K. I mean, this could be the open set of this. So this whole thing is a graph, this thing. So this is my U tilde. U tilde. So since I'm approximating functions, I put temporally this inside of a little open set. I do my approximation like this. So I find an algebraic set inside of Rn cross Rm, and the smooth function phi, and the diffeomorphism define a graph of the smooth function, which is diffeomorphic to a copy of this. So this is a graph. This is a graph. So then F projection F project pi is approximates P. This is so this is condition 1. So this is condition 1, diffeomorphic. 2, this composition approximates this polynomial. This is a polynomial. 3, L cross 0 is in U tilde. In other words, P, L cross 0 is equal to U. Now, is that clear what I'm saying? I'm writing this for students. It's very concrete. I have a non-singular algebraic set, a little open set U, that inside of it is a K, and I want to approximate, and this F is polynomial already on L. I want to approximate F by a polynomial such a way that it will keep that property. New polynomial still will be the same values as F on L. So the way it is done that you find an algebraic set, you're going a higher dimension, Rn cross Rm, and then there's this projection, find the diffeomorphism, a little copy of U, which is U tilde, is given by the graph of some function. So if you think of it, phi is like some function like this, and I'm taking graph of it. And then this is a non-singular algebraic set. Z can have singularities outside, but there's a nice non-singular piece of it, and then that phi defines a diffeomorphism from this open neighborhood, that open neighborhood, and then that's a projection. The projection lies over that. So and there's a polynomial from here to W, okay, such that when you take a project and F, this is close to the polynomial, such that this guy didn't. I mean, I didn't draw a nice picture. U tilde, this yellow should coincide with this yellow. So I approximated F by polynomial without moving L. F was already a polynomial on L. So this is our normalization theorem, which we use all the time in many contexts with Henry King. And let me outline the proof of it. Is this clear to everyone? It's just simple. I mean, ideally, you would like to find some polynomial approximating F, keeping F, but you cannot do that in here. You find a copy of this upstairs, this and a copy of this open set around this, and this sits inside of an algebraic sheet, algebraic set. In here, you find the polynomial going here to W, and on P at L coincides with F at L, which was a polynomial already. So, I mean, this is a non-singular algebraic set. Suppose it's given by vanishing of some polynomial, delta x equal to 0, some polynomial. So what you would like to do is you have this U, and you have L, and then there was a function in here. You just approximate by this polynomial, and then this is now I'm drawing. Suppose this is like Rm, and M was a non-singular algebraic set in there, so this is a non-singular algebraic set W. And this guy, F is taking this to here, F. So you approximate this by a polynomial, by keeping, there's no problem, because this is what I mentioned in the beginning. But the problem is once I approximate this by P, so here, if you take a point, some point in here, this point will be here because you are approximating some function going to Rm. So the function will live in Rm, not on W. The original function was on W. How can I solve this problem? Well, one way is you can project this normal projection, but it kills polynomial property. Function is no longer polynomial. It's a Nash function. That's what Nash proved. In his context, he did this technique. In projecting it, he get a Nash function, and zeros of it is not an algebraic set. It's a sheet of an algebraic set. He needed to separate them. So now I will tell you how to solve this problem. Here's a solution. Z, so I define Z. This is a set of X, Y in Rn. So I will tell you exactly what this Z is. Once you see this Z, then you realize, this P is taking this U tilde right on the nose to W. It's also approximating it. And you do this. So first I approximate this by G. Okay, G approximate F, G restricted to L is U. So that's the previous lemma. It's a polynomial. I switch from P to G because that's what my notes says. So here's an equation. So Gx plus Y is in W, and delta Gx plus Y times Y. I should call this delta. I mean, this is some polynomial like this is equal to Y. Let me tell you what this is. So this is an algebraic condition. So this is what your Gx is. Okay? This says if you add Gx to some vector y, this is y, so Gx plus y, this thing is Gx plus y. In here.
There's no fixed direction to add.
Yeah, so there's no fixed direction. So add some vector. And that's such that this will, Gx, add a vector, should be W. This is an algebraic condition, because these are polynomials, they satisfy this polynomial. This says that this should be perpendicular to this. So what does that mean? Recall Gauss map. So this is W. W is inside of W. So let's call the K is M minus W. This is a codimension. So there's a Gauss map. K planes are M space. It's a Gauss map. which is algebraic. And then a tubular neighborhood. It's a tubular neighborhood. There's a little tube around this, and there's a normal bundle map. There's a bundle over this. Remember, every time you have a closed smooth submanifold, if this manifold happens to be non-singular algebraic, the Gauss map, which takes point normal plane, is an algebraic entire rational function, and the map, the classifying map of the normal bundle is an entire rational function. So I mean, these things. These things were like. So this is delta. So the and then this means projection of y on that normal plane. You get the y. So that means this y is perpendicular to this. Remember equations of this. This equations of this symmetric. This is n by m symmetric matrix. A transpose is equal to a square is equal to a, trace a is equal to k. This is non-singular equations of this. This guy is given by some a and some y inside of this is g. Rm cross Rm, such that such that ay is equal to y. Right? These are the non-singular equations of my Grassmannian, and this is the universal bundle over it. It's obtained by universal bundle is a point in Grassmannian, it's a tautological bundle, and the point in Rm such that when you project y to a, you get y itself, normal. So ay is equal to y. This is an algebraic condition. So and this says that y is perpendicular to w at gx plus y. So this is gx plus y. So take y any point. Huh? Now I'm fixing the direction. But I did it such a way that it's all algebraic. Everything algebraic. There's no by hand projection, nothing. Everything given by polynomials. So here I produce non-singular algebraic Z. It can have many pieces, but I need to find a diffeomorphism. I mean, I need to find U tilde. I need to find some diffeomorphism to U. I mean, there's a diffeomorphism when you pick y small, so like this. When you take y coordinates very small, there's a unique closest distance. So when you tilde, when you let y coordinate near the origin, then given x, there's a unique y. So when x, there exists a unique y. So you can call this yx. In fact, this is my phi's. I call this phi of x. So I find the diffeomorphism from the little tubular neighborhood of U around my k and upstairs in the graph. This is such that xy satisfies this. So I found the diffeomorphism, this one. Is that clear? So this is a very fundamental normalization theorem. I will use this over and over again in many different contexts. In one case, F, I mean here, F is a map in the, I will prove now Nash's theorem when taking W itself to be a Grassmannian variety. And then I will also apply this to F. F is like U is going to be, is K going to be smooth manifold. F is going to be immersing the smooth manifold Euclidean space. And then I apply this theorem, and I prove the image of P will be what I want. And then for that, I need to use some techniques about complexification. Algebraic condition. Any questions about this before I erase? Because I will come back to this. Map. So the basic thing is I started with some compact set or some open set around that compact set and a map, and this map has to be polynomial on some non-singular algebraic set. I can approximate this by polynomial, keeping value of f on L, provided if you let me add some dimensions in here and replace u by this. Okay. I mean, the easy version of it is, now I will do Nash theorem, but let me mention the simplest version. When this manifold, I mean, this was like a neighborhood of K. K is going to be smooth manifold, and the W is going to be Grassmannian, and then this map around this will be a normal bundle map, Grassmannian. Simplest version is manifold as trivial normal bundle. In this case, you don't have Grassmannian, you just have the complete intersection case. We saw that if you have a manifold last time, there exists exotic. So just 16-dimensional exotic split arbitrary, which is not isotopic to complete intersection. This shows me even when you have a manifold with normal bundle, even non-trivial, I'm not going to be able to solve this by just by transversality to make whole manifold algebraic. Okay. So theorem, analyze Nash. Given L non-singular. Non-singular algebraic subset of W. W is the open non-singular algebraic set. This is I think W M. This is closed smooth. So I have a closed smooth submanifold, and there's a little open subset of it, and inside of that open subset I have a non-singular algebraic set in Rn. Then we can approximate M, approximate epsilon isotopy. Vm, where this is a component of an algebraic set, a non-singular. For the algebraic set. So I have a smooth manifold sitting inside of Rn. I have this L, I think let me just say this is non-singular algebraic set. So I have a little non-singular algebraic set here around this, and also some non-singular algebraic subsets. I can make everything a V. I can find V. Let's do that blue. So I find the blue an algebraic set, but it's V itself is a component of a non-singular algebraic set, a non-singular component of an algebraic set. It could have all the other components, lower dimensions, and this is taking place after I stabilize it. So this is meshes. I'm getting meshes to it. Basically, every smooth manifold. First reading, just forget about L. Just take closed manifold, and it is diffeomorphic to component of an algebraic set. So how do you prove this? I did all the homework to do this carefully. So proof. So you take M. So in the beginning, you can forget this L business. So I have an M, take an open neighborhood, open tubular neighborhood in Rn. And F, you take F to E. So the codimension n minus m is k codimension. Codimension of m. You just take a universal bundle. You take a map such that this is the Grassmannian variety. So you have a map, the Gauss map. You write the tubular neighborhood of this Gauss map. You map that tubular neighborhood, normal bundle map, the Gauss map to a universal bundle. And then from the construction, this guy is transversal. F is transversal to here. Here. In fact, M is so this is the elementary differential topology. You have a closed smooth submanifold, take a tube around this, map this tube to universal, the tautological tautological bundle over Grassmannians such that F is defined in here, which is transversal to this. If restriction goes there. Can assume if restricted L is U. Because it's just a smooth map. Any polynomial. I'm putting as an extra thing in case you want to use it. And then normalization. Normalization. Apply normalization. I just mentioned to you. You have Rn cross Rs. You have U tilde and a projection pi going to Rn. And then you have U. U was tubular neighborhood of this guy. And then you have a projection, restriction of this projection. And that was just my phi, diffeomorphism in here. And there's my map F to E K Rn, which sits GK Rn. This map is transversal to transverse inverse images of my manifold. Then I can find the polynomial map here. Polynomial. Maybe I should say anti-rational. I'm mixing them sometimes because anti-rational for me is just a polynomial or polynomial, and the denominator never zero. So you have a polynomial map like this, and then in fact this is what subset of Z. This is an algebraic set. So this is a little non-singular part of this U tilde. U tilde is a diffeomorphic to U, use a tuple neighborhood of my manifold. So there's a polynomial. So this a copy of my manifold is in here. So I have a polynomial map. Inverse image of GKRM is my M. So in fact, F composed pi is approximating P, and L cross Z fixing L U tilde. So these are the conditions. So this is the relative condition. If I want to, I can approximate this like this. So to sum up, my U tilde sum x px x is in U. This was a tubular neighborhood of M. And then by transversality, so this is diffeomorphic to U, by transversality, P inverse U tilde is pi inverse F inverse this is M. I mean, all I'm saying is these are diffeomorphic in here. So this map approximates this pi composed by F. So this is because this is this inverse image of this was M, but then you are pulling by pi upstairs. You get a diffeomorphic copy of your manifold. Now, this is a polynomial. This is given algebraic variety. So I'm down. So I prove that every closed smooth manifold is a component of a non-singular algebraic set. Now there are many other versions of this theorem. Can you do it without stabilizing in here? Can you do this in a non-singular algebraic set if my smooth manifold already sitting in some non-singular algebraic set, not necessarily Euclidean space? Can I do it if you have some not inside of like projective space? All these questions. So it turns out that you cannot generalize this if this is replaced by a non-singular algebraic set. To do this, you need that non-singular algebraic set to have total algebraic homology. How much time do I have? How much?
30 minutes. 30 minutes.
30 minutes. Oh, okay. Very good. Very good. So 10, 3:30. Okay, very good. Okay. So now let me remind you. Which I did before, algebraic homology. So V non-singular algebraic set. I defined to you last time. So every algebraic set carries a, inside of any non-singular algebraic set or Rn, carries a top homology. Top homology class, a k-dimensional algebraic set. Kth homology is Z2 with Z2 coefficients because of this even Euler characteristic condition. So that's an algebraic homology of and I also define A these are the ones that are generated by non-singular algebraic subvarieties. Here. This is all algebraic subvarieties in here. And let me just mention one theorem. Algebraic Stinrad representation. So stuff I'm talking here is from number 22. The paper appeared in American Journal of Math. Also, right after that, Invenciones of Math, studying of these algebraic cycles. So the simple thing is given, so what is Stinrad representable to say? If you have a homology class, Z2 homology class, it can be represented by a mapping from a smooth, closed smooth manifold by some map as an image of fundamental class. There's an algebraic version of this. So this is a non-singular algebraic set. Then there exists algebraic multiple of again, algebraic multiple map means composition of blowing ups, centers, low-dimensional centers. If I have an algebraic subset, algebraic multiple map of that algebraic set means blowing up, sequence of blowing ups, centers dimension less than the dimension of that algebraic subset. Then there's something called uzun blow up in our papers. Uzun blow up, uzun means long. Uzun blow up means you blow up and then you are allowed to change by rational diffeomorphism. You know, you just find a rational isomorphism. You change this algebraic set by some rational, I guess birational diffeomorphism, then you blow up. They replace by birational diffeomorphism, then blow up. We call this uzun blow-ups. Sometimes you have to use this in these papers. So that's, but here I'm using an algebraic multi-blow-up. There is an algebraic multi-blow-up along, so as a given so let's forgive us in here. Given non-singular algebraic set in a class, homology class, k-dimensional homology class, and then algebraic multiple blow-up along centers of dimension less than k, and a non-singular effect in here. A non-singular algebraic set Z0 is a union of connected so that represents this class. So Stinrad representability theorem, there are many versions over Z and or Z2, but the easiest version is over Z2. Over Z, there are obstructions even doing this. If you have a Z2 class, then non-singular algebraic set, there's a multiple blowing up along centers of dimension less than k, and such that you have a non-singular algebraic subset, and some component of it, when you restrict the projection to some component of it, this is what represents this class theta. A closed map from closed manifold to a manifold, we say it represents homology class if it takes the fundamental class of that map into your homology class theta. So this it's important. This is a union of connected components. It's important in general. It's not equal to Z0. So definition. we say V is total algebraic. We call algebraic, non-singular algebraic set as total algebraic homology if all homology cycles are algebraic, can be represented as algebraic subsets. So in fact, this implies that it is represented by algebraic subsets. Why is that? Because, I mean, I have here, I have a map. So I have a Q representing, so pick smooth. Pick k-dimensional smooth manifold representing it. This is still not representability. Representability. This is always true over Z2. In Z cases, you have counterexamples. We pick such a thing. So now we apply this theorem. What did we prove? I mean, this is V non-singular algebraic set. Remember, this was W. And then I can find the diffeomorphism here. Q tilde. This is a component of a non-singular algebraic set. There's a P in here. Okay? And now this is a polynomial, anti-irrational. And let me draw with this yellow. Now I'm applying this normalization theorem to this one. It's a component, non-singular. Component of an algebraic and algebraic set, non-singular. Here. And now this going into here. Now I would like to say that algebraic homology itself, when I look at them, I should see algebraic subset. Well, I take this image of an algebraic set under polynomial map is not algebraic. You take the Zariski closure. You take the Zariski closure. But remember what theorem says. If you take Zariski closure of an algebraic set under polynomial map, if you have the property that Euler class of inverse image of every point is odd, then the new components you introduce, this is the new component you introduce, is a lower dimensional. Do I have this condition that inverse image of points are odd Euler characteristic? Well, this is representing Z2 homology class. By definition, it's a degree 1 Z2 homology map. So therefore, by definition, inverse image of points must have odd Euler characteristic. So then you have, then you look at the image of this. Now you represent this class, the elements of these things, actual algebraic subsets. And then after you've done this, I'm simplifying this proof. I think this proof from this American Journal of Math paper. Then you blow up. Wait, blow up. You apply resolution of singularity theorem. Then this is you have this situation. Is it Z tilde here? There's one component. I mean, there in blow up, you might have some other components appearing in here, coming from the centers, but you are only interested in this piece. Union of connected components of Z. So you, in fact, you can make Z2, algebraic Z2 homology, actual represent actual algebraic subsets. Furthermore, by blowing up, I can make this thing V tilde image of a non-singular component of a non-singular algebraic set in here. you cannot make it, there are examples, so there are examples of homology classes which cannot, this cannot be done because this is general, is not equal. So next I want to give some examples how to construct these transcendental homology. Are there any questions about this? So the techniques are not difficult. I'm using Hironaka resolution of singularities, basically. Here's some examples. Let me just tell you the importance of theorem. So given most smooth effect every closed smooth is isotopic to the non-singular algebraic subset of V cross Rn for some if and only if V has totally algebraic homology. So before I mentioned this theorem when V was Rn, so I proved that every manifold can be represented as a component of a non-singular algebraic set. Very soon I will prove that it can be represented by non-singular points of a non-singular algebraic set. But before going to the difficult theorem, I'm telling you this more advanced theorem. A non-singular algebraic set is given. Every closed smooth manifold can be moved to a non-singular algebraic subset of V cross Rn if and only if V has total algebraic homology. And the way, I mean, all you need is Bordism plus of M in V must have algebraic representative, then it can be moved to non-singular algebraic set in here. This is kind of slick way of doing. Every M can be done if V has a non-singular algebraic homology. Let me also mention, for comparison, the advanced version of this theorem. Every closed, smooth, is epsilon isotopic to non-singular components of an algebraic set. Let me make a definition. V0 is a non-singular components points of V. So this is my convention. V0 means non-singular points of V. So this theorem is much, much more difficult than this one. So here I have a smooth manifold. In Euclidean space, I have a smooth manifold M. I can move this to non-singular, epsilon isotope to non-singular point of an algebraic set. That means I have an algebraic set This is my V. These are the non-singular points of my algebraic set. So yeah, I have an algebraic set. Non-singular points is a little isotopic copy of M, but they are little microbes, little lower dimensional things. These are the singular points. And now it's an open problem whether you can remove these things. And I don't know how to do this. So, I mean, in fact, this can be written because these are singular points. These are singular points of singular point of this. So they can be written like G, some Q, some polynomial, vanishing of polynomial equations. And V is given by vanishing of some polynomial equation. So corollary of this is every closed smooth is isotopic to a non-singular algebraic subset of Rn plus 1. What's the idea? I mean, you know the proof of this already. I have here little microbes in here, right? This is my Rn. You cross this Rn with R. I told you, Zariski open sets become algebraic once you go one higher dimension. You write equations of this in an algebraic set that will look like, and then they will go to infinity. Call this V, so this is V, and this is called V tilde. What is V tilde? Equation of V tilde is x comma t Rn cross R. So the x coordinate given by the vanishing of equations of V, Px equal to 0. And the t coordinates, you write Tqx equal to 1. So you're writing t coordinate is like 1 over Qx. So when you approach x points in here, Q is 0. So you are in this new coordinate, t is 1 over Qx. When you approach in here, they go to infinity. So you push them to infinity. So you are almost there. Every closed smooth manifold can be isotopic to non-singular algebraic subset of this. In fact, there is a version, there's a more advanced version which appeared now defunct journal, Topology. You can replace this by an immersion. Non-sing means inverse manifold non-sing means just like usual definition, except in the singular points are intersecting sheets, non-singular sheets. You can make a definition what non-singular means in this category. So this works, and there's one advanced version of this theorem. Every closed is isotopic, epsilon isotopic to a non-singular algebraic subset V. For emphasis, that with yellow, V in Rm. If and only if the Bordism class is algebraic. So that means if this smooth manifold, there's a smooth submanifold, if you can find some Bordism far away, some non-singular algebraic set, then you can solve this problem completely. So if you can generate enough algebraic subsets such that this thing is Borden to that, in fact, there's a version of this with immersion. We can talk about Bordism of immersions. So this is Bordism. I don't know what notation. It's Bordism of Rn with algebraic Bordism. So in particular, this says that I give you a smooth manifold. I'm asking you to isotope an algebraic set. If you are by some luck, if you can put this in one lower dimensional Euclidean space, or not even by isotope, by Bordism, just crazy Bordism, in some lower dimensional algebraic set. Therefore, this algebraic set there can be made algebraic one higher dimension. So therefore, this guy is Borden to an algebraic set. Therefore, this guy can be epsilon isotopic algebraic set. Do you get the logic? So suppose, so I have a non-singular algebraic set in Rn. Suppose I'm able to board this to an algebraic, forget even algebraic set. Suppose I'm able to board this to lower dimensional Euclidean space. I have an m-dimensional smooth manifold. Suppose by Bordism, I deform it, I put it in Rn minus 1. So now I apply that guy in Rn minus 1, this theorem. Because I board my manifold to some submanifold in Rn minus 1, and by this theorem, that manifold is epsilon isotopic to algebraic set one higher dimension, Rm. So I found in a Bordism class of this manifold contains algebraic representative. Therefore, you use this theorem to make it epsilon isotopic to algebraic set. You immediately see there is a lot of interesting algebraic topology problem comes out of it. I give you a smooth submanifold of Rn. When is this Borden to lower dimensional, smooth submanifold, same dimensional, in the Bordism class, in one lower dimensional? When can you, through its Bordism, put in one lower dimensional Euclidean space? And this is a theorem about some homotopy groups of Thom spaces. And same, same version is true for emergence. So I don't know how much people study emergence these days. Maybe they don't study emergent theory. There's a beautiful theory by Smale, Hirsch, and Gromov, and finally became H principle. So it's to say that m-dimensional submanifold of Rn Borden to one lower dimensional means some homotopy groups of Thom space lives in the image of suspension map. But if you are interested in only immersion, so if this guy was immersing in the Bordism one lower dimensional Euclidean space, it means the normal bundle of this manifold must split a trivial line bundle. Because if this manifold sitting in one lower dimensional Euclidean space, normal bundle, one direction will be trivial, right? So the H principle tells you that if you know that fact, if you have a smooth manifold, normal bundle contains a trivial line bundle, you can immerse in one lower dimension. It's a beautiful theorem, H principle. In fact, if your normal bundle splits k-dimensional trivial bundle, you can immerse you go k down, n minus k-dimensional Euclidean space. It's a Smale-Hirsch theory made more advanced. So then you have these questions. Then there's a corresponding algebraic topological theorem corresponding to that. So the corollary, let me say the corollary of this. This is if Bordism class, if cabots to, if M cabots through cabordism to some manifold in Rn minus 1, then M is epsilon isotopic to a non-singular algebraic subset. And then, again, the proofs steps are when it covers in here. By that theorem, this guy can come back in Rn as an algebraic subset. Now, then I found that in the cobordism class of M contains algebraic subset. Then I use this one. If cobordism class contains algebraic subset, so then it itself can be isotope to algebraic subset. So I asked this question to homotopy theorists. They don't believe this is related to algebraic geometry, real algebraic geometry, but it is a pure algebraic topology problem that can be. So since the remaining 10 minutes, rather than proving technical theorems, let me just say general things about algebraic topology. So it's cobordism classes or boardism classes of k-dimensional closed submanifolds. Okay, codimensional. Let's make it codimensional. I mean, let me just call this K. All right. So the elements in here is a k-dimensional submanifold. Two of them are equivalent if there's a k plus one dimensional submanifold in Rn cross I. One end is one, the other end is the. This thing is that there's a one-to-one correspondence with pi m or k. It's a thumb space. What's thumb space? I mean, it's very easy. Remember, I mentioned codimension k. So this is, I was talking about Gauss map, k-dimensional planes, and this is the k-dimensional canonical bundle over this. It sits like this canonical bundle. This MOK is the one-point compactification of this. If this guy looks like this, and then this is like a bundle. So this is like this. This is like that. This is an RK bundle. Maybe I should write it as a bundle. That's an RK bundle. It's a universal bundle in here. If you one-point compactify it, so if you take this this is called thumb space, MOK. It's very simple. I mean, it's really, to be honest, MOK has to be when M going to infinity in the stable case. So this is a famous thumb space. You have a bundle over a closed manifold, compact closed manifold. You collapse the infinity to point. Or you can think of this like a disk bundle. You collapse the sphere bundle to point. This is the MOK. So there's this. So then, so the you look at the ones that come from Rn minus 1. These are cobordism classes of codimension K submanifolds of Rm. Now I look at the cobordism classes of codimension K submanifolds of Rn minus, did I call them M? Rm minus 1. This thing can be corresponds to image of suspension. So there's a suspension map. There's a suspension map. it's easy algebraic topology. You can characterize this by the image of suspension map. Remember, I proved some theorems about complete intersections. Smooth manifolds are complete intersection. If it's a Bordism class, comes from the suspension. That corresponds to the case when this is a trivial bundle. Time space is just a sphere. It's just a sphere. You know, I said the exotic sphere corresponds to the element of this exotic sphere, trivial normal bundle. If it's a complete intersection, it has to be in the image of suspension. So then here, I don't know what notation I should use. Let's go like this. Cobordism classes. Of inverse codimension K submanifolds. There's a one-to-one correspondence with this one, and with pi k loop infinity. Suspension infinity MOK. Don't be afraid of this. This means you suspend many times, n times, and suspend. Then you take a looping n times, and then you do MOK. Okay. And so the ones come from Rm minus 1. Just like in here, the immersions, they come from Rm minus 1. Because if you have codimension K immersion of Rm minus 1, you can go to codimension K immersion of Rm. They come from the image of suspension. So there's a suspension map, pi k minus 1. Something like this. So there is a corresponding algebraic topology problems. I will tell you how to attack them. In fact, when I was lecturing something like this in Michigan, Raimondo was there, and our class there was an expert in Asadi, whose thesis was about proving which, from Manchester PhD, which elements of this come from suspension. But he's so algebraic, we couldn't communicate. So we're still talking to that guy, and there's some English people that study this thing. Okay. So how much time do I have? Okay, now continue next time. Thank you very much.
So I think we have a call right now. You can continue discussing yourself if you want to.
Okay.
Thank you.
Thank you.